welcome to my YouTube channel. And today I will be implementing what I learned on Kaggle, Intro to Machine Learning. And when you are done with everything, you will be required to make a submission for this project, that's housing price competition, right? Before that, when you are done with the course, you would have been able to learn basic machine learning stuff. You will learn random forest, you will learn decision trees and all that. And you need to still improve your data set. You need to train your model to make it much more compactable, and then you submit it on Kaggle for your grading. And that is what we'll be doing today. Before we begin, you would have to download the train CSV file, the test CSV file, and all that. So you just go to, after the overview, you go to data and you scroll down. Yes, so this is your data description. Just a description of what you'll be doing. Sample submission will give you a sample of how you should submit your prediction. So it will be in ID and then sale price. So your model should be able to determine or predict the sale price of the housing project with this ID. This is just a sample. This will be your test CSV file. Test CSV file is what we will use to test our model to see if the predictions are doing well and all that. The train CSV file will be what we'll use to train our model. So let's dive into it. I'm using Google Colab, and as you can see, I named here Kaggle House Pricing Competition. That's alright. I'll just take it like that, and then I uploaded the train and then the test CSV file here. To import pandas as PD. Yeah. Alright, so we need to import our pandas and name it as PD for easy aliases and where we want to call it and all that. And so I would create a variable named MB and from that, and I would need to copy the path here and then show it here. So So I imported my pandas and I named it as PD, and I created a variable to store the file path, and I created another variable MB data to read my file. That's the train CSV file. So in order to see the things we have or the stuff in a dataset, I need to call the describe function. So I would see what it consists of. So As you can see, we have ID, MS, subclass, launch, frontage. It is a whole lot, right? It's a whole lot. And then count, which means we have 1,460 houses to predict, right? So this is just a summary of the data set, or what it includes here. This is the mean for everything, the minimum, the maximum, 75%, and all that, right? We have lots of columns, and if I want to actually see the columns we have here, I just have to change it to so let's just run this in. Oh yes, I had to just take that off. So we have a lot of columns. That is the features associated with it. However, we wouldn't be needing all these things. We will just need the most important ones for training our data set. There are certain things or certain features if you include in it, it makes your model predict certain things like unrelated information. It makes it quite redundant. So we would have to, take certain things out here in training our model and then focus on the most important part. Like this screen porch and pool area and garage finish, garage cars, it wouldn't be needed to actually predict the prices of our housing projects, right? So we would create a feature and then take off all this. So this is the first part. We imported our pandas, created a file path, we read it, and then mb underscore data dot describe would give us overview of what our file includes, and then those columns would give us a list of the columns related, the list of columns that are included in this train CSV file. Forgive me if my voice is a little bit rough. I am not actually doing well. I have been discharged from the hospital and all that. Sorry. Alright, so the next thing we are going to do is to select a subset of our data, right? So we would use the dot notation to select the part where we want to predict answers for. That is the price column, where we want to predict answers. To determine the price for the house. So in this case, the sale price. We want our model to predict the sale price of the houses based on data sets that are available. So we train our model based on this, and then we use the test the CSV file to test our model if it will get it right. So can you please create a variable? Right, so we've selected the sale price. That's the column we want our model to determine prices for. We also need to create features. When we talk about features are basically the characteristics that are associated with the house, Right, so we want our model to determine the sale price for a house, but depending on certain features, so probably depending on the room, the bathroom, the land size, the latitude, the longitude, the lot area, and all of that. Certain things are not necessary, wouldn't even include it, like year built and all that, are not really necessary in determining the price of a home. So that's what we will do. Okay, so we're going to MB underscore features random disconnected. So we are going to write a list of the columns that will be needed in determining the price of a home. That would enable our model to predict the price of a new data set. So certain things are not necessary, but some certain things are really needed in this. So let's just do it. We need rooms. Okay, so we've written our features, and we are going to name it X and B. So we need to see we need to review our data. So X dot describe. Let's see. Okay. There's an error. Attribute error here. Right. This other project has no. Right. So yes. So we've now had a review of our data. So what we did here is to basically create a variable, and a variable that takes into consideration our sale price. That's a variable y that is for our target. So our target is to determine the sale price, right? That's what we've done here. And this is just a graph of what it entails. And we also created the variable features, which includes the things that are related to or are related in a home that enables you to determine the sale price. So we created another variable x, and we assigned it to MB data. MB data is our variable here, and our MB data includes our red CSV for using pandas, right? So and so it has, and it includes the features. So X dot describe will show us a review of our data. So let's see, X dot head should give us our first 5. So 0, 1, 2, 3, 4. Give us our first 5, and based on the features you can see overall wow, it's number, the total, whatever, full back, bedroom, AB above ground, and all that. So let's just make it probably should show us the first 20. a first training data set. So we have our first training data set here. Right. So this is what we've done here, and this is not all. We are now getting to the interesting part. That is, we are going to build our model. We are going to fit our model or train it using a trained data set, and then we are going to test it using our test data set. That's what we'll be doing next. The reason why we will be training it using our trained data set and testing it with our test data set is because if we train it with our trained data set and we test it with the same data set, it will give us accurate results, which is deceptive, because it wouldn't be able to give you predictions when you give it a new data set it hasn't seen. And that isn't the main purpose of ML. So we would train it using this and then we will test it using this. Let's get to it. Building our first model, and then this is a more like a beginner level myself. So I'm going to start with the basic ones to the advanced ones. The reason why, as we move forward, the basic parts aren't necessary because they have some flaws. So the advanced ones are really good, like the random forest is better than the decision tree regressor. So this is what we are going to do. From skeleton, that's a tree. I'm going to import decision tree regressor, which is already here. Then we are going to define our model. So mb underscore model will be equal to our decision tree. So we are using random state because we want our model to be consistent in its working environment. So we are now going to fit our model. So mb underscore model dot fit. Fit is basically retraining the model, and we are going to train it with x and y. This is bad because we are going to train it with the same model, and then we are going to predict it using the same training data set, which is bad, right? However, for us to understand why it is bad, we are going to do it, right? So let's make our prediction. So let me just print making predictions for the following 10 houses. Is it 10, right? Yeah, we are going to do it then. I print As I said, this is bad because we are fitting or we are training the model using our trained CSV dataset, and we are also predicting it using the same trained dataset, which makes it very bad. But let's just do it anyway so you understand. So, making predictions for the following houses. These are the first 10 houses. This is the raw data set, and then the predictions for it is this. Right. The predictions are, so it says that the first house will have a price of 208,500. The second one is 281,500. The third is 223,500, and all that. Let's just minimize this to 5 to make everything 5. So I just want to, make the reading well. So I'm just going to include empty spaces here. So, yeah. The reason why we have it being written here is these are our features: overall qual, bedroom, garage, cars, garage area, built, fireplaces, slot area. These are our features. So these are our prediction for the first houses. So as I said before, this is bad because we are training it with the same data set, and then we are predicting it with the same data set, which automatically makes the model, predict it on an accurate basis. Model validation, that is a mean absolute error, MEE, and this will help us, calculate or understand the reason why I am saying this is wrong. So what it does is basically let's go here, and you will see what MAES. Alright, so the mean absolute error, this is what it does. So the prediction error for each house will be equal to actual minus predicted. So if a house costs $150,000 and you predicted it will cost $100,000, the error is $400,000. Right? So with this, we just take the absolute value of the error, that's the positive value. We don't take any negative stuff. So to calculate it, we need to build a model, and we'll do a lot of stuff. So we are going to implement what this is in over here, so it would make sense. So we are going to implement the model validation. The reason why I am saying what we did here is actually wrong. We are going to calculate our mean absolute error to know what this does. So let's get into it. Okay, so we have our model, so let's calculate our mean absolute error. So from our SQ line, this is circuit line dot matrix. This is a library that contains the mean absolute error. So mean absolute we're going to create a variable called predicted home prices because mb.model dot So what we've done is we've imported from the library that contains the mean absolute error. We've created a variable, predicted home prices, and we equated it to our MB model.predict. This is our MB model.predict. Okay, so this is our MB model. Where is our model? Yes, MB model. That's equal to our decision tree percent all that. And we're predicting it with X. The dot head 5 means you are just doing the first 5. Without the dot head, we are doing it for all the data. So this is what we've done by. So our mean absolute error will take the predicted home prices and that of the original prices, and then it calculates the average error. So in this case where we had this issue of getting an error that is $50,000. If we had first case $50,000, second case $100,000, third case $20,000, so the mean will be these three instances divided by 3. That will give us our mean absolute error. So this is what it is doing. We are taking our predicted home prices versus the actual sale prices to calculate our mean absolute error. Oh, okay. So, metrics. Alright. Predicted MB is not defined. Okay, so real quick, let's fix this. Alright, so we fix this issue this is our mean absolute error. We are getting 19.34 whatever, which is wrong because we basically trained our model using our trained data set and we are predicting it using that same data set. So the margin of error is very less, right? Which makes this using this phase or this approach very wrong. So what we are going to do is in the next phase we are going to split it into two. Our training data set is we are going to split it into two, where we would have some parts for training and then some other parts for testing, right? And we are going to do it using a train test split, which is available in sklearn. We just have to import the class that contains it, that's the model selection. So in our next phase, that's what we'll be doing, and we are going to split it into two for now. So let's just get into it. So import our test our test split, import training, so this will enable us to split the data into training and validation data for both features and target. Remember, features are the characteristics and the target is what we are building the model to predict prices for. So that will be our target. In this case, it is the sale price. That is our target. So that's what we'll be doing. So I'm going to name it train X X. Right. So train X means train data and val X is validation. So train Y and val Y. And will be equal to our train split state equal 0. Alright, so our X, this X is takes care of the columns we use to make the predictions. That's our features, and then our Y is our target. That's the sale price. Our random state equals 0. This makes sure that we get the same split every time we run the code. Without this different split, we will get different splits each time. That would result in different results, right? But this claim random state equals 0 makes our prediction very consistent. So that is basically the use of this. So I'm going to also define a model and then make predictions again. Right. I think I did it here. So I'm just going to copy. I'm just going to copy this and then paste it. In this case, we are not using X and Y. We are just going to use our train X and our train Y. This X and Y represent the full data set. However, we divided it into train and then test data set. Right. So this is what we'll be doing. We're going to do it this way and we're going to make a prediction. So I'm going to call it val prediction. MB model predict this. Alright, let me explain this real quick. So we are making a validation prediction. This is the new prediction we are making, and however we are predicting it using our validation X. Right, it's not our training X, our validation X. This should be able to give us predict our validation Y. No, this should be able to give us our val predictions. Don't forget that we are only able to predict for an answer using our features. X represents features, Y represents our target. Yes. So validation X is a piece of data that we'll be using to validate our model, and then the train X is what we are using to train our model. So we want our model to make a prediction. However, we wouldn't be using what we use to train our model. Unlike the first one, where we we fitted our model using the whole data set, and we predicted using the same thing we used to train our model. This is what we did in the first one. However, in this session, we are not doing it that way. We are training it using our train data set, and we are predicting it using our validation one. We split it into two. So we are going to print mean absolute error using our validation y to our bar prediction. That's what we'll be doing. So let's just run it. So our mean absolute error, don't forget to calculate the differences between your predicted value and the actual value. For if it is 5 columns you want, for that 5, and it calculates the average, right? So that is what the mean absolute error does here. Let's just run this to see how far we can get. Right. So in here we are getting 26,461, which is, even though it is high, it is much better than this. But this mark is actually very deceptive. However, this shows honesty, right? So this is one way you need to go about it. There is also another way where we take into consideration overfitting and underfitting, right? So let me just go through it a little bit. Overfitting and underfitting, and we have an important phase called our sweet spot. Let me just go back. Alright. So with decision trees, as our tree is getting deeper, let's say beneath our leaf we get like 10 leaves instead of this 4. It results in a phase called overfitting, because the model matches the training data almost perfectly, but it makes it very poor on validation and other data. So let's just read what overfitting and underfitting is, right? Alright, so now that you have a reliable way to measure model accuracy, you can experiment with alternative model and see which gives the best prediction. But what alternative do you have for models? So scikit documentation, all that. So this is a relatively shallow tree. We say it is shallow because it doesn't have much more leaves beneath here. It makes it very shallow. So in practice, it's uncommon for a tree to have 10 splits between the top level and the leaf. As a tree gets deeper, the data set gets sliced up into leaves with fewer houses. If a tree only had one split, it divides the data into 2 groups. If each group is split again, it would have 4 groups of 1. Splitting each of those again would create 8 groups. If we keep doubling the number of groups by adding more splits at each level, we will have 2 to 10 groups of houses by the time. So basically what it's trying to say is as our shallow tree gets in more deeper. So let's say here we also have an arrow here that gives us another leaf. So this we also have 2, this 2, this 2, this 2, 8, and out of that 8, 2, 2, 2. So it makes it very depth. It makes it move from a shallow tree to a depth one. However, it also has its side effects, right? It says that when we divide the houses amongst many leaves, we have fewer houses in each leaf. Leaves with very few houses will make predictions that are quite close to those from actual values, but they may make very unreliable prediction for new data. So, what overfitting and underfitting is? Overfitting is when the model will be able to match the training data perfectly, but it does poor in validation, like what we did here, the initial one, where we tested our data set using the same, we trained our model using the same thing, and then we predicted using that same training data. This is overfitting, right? Because it will do very well here. However, if we tend to use a different data set for it, it wouldn't work. It will give deceptive results. That is overfitting. However, underfitting is one case where the model fails to capture important distinctions and patterns in the data. So it performs poorly even in training data. So in a case where your model, you've trained it with whatever you need to do it, but probably, let's say, a house with bedroom above ground, let's say 4, and the price is, let's say, $24,000. However, it has 3 garage cars, and then 1 room with bedroom above ground, the same, but it has like just 1 garage car. It would also price the same. It will also give you the same price. Let's say if it's 25,000 for one with 3 bedroom and 3 bedroom and then 2 garage, it will give you the same price for 3 bedroom with probably, let's say, 3 garage, because it failed to learn certain patterns. It failed to learn patterns in the data set, so it tends to give so many bad results. But there is a solution using the mean absolute error. So our blue line is for our training, right? And it shows error on data the model learned from. That's our training data, and it always goes down as the tree gets complex. So it went down as our tree is getting complex, moving from left to right. And the danger is it makes overfitting look good. Right. We said overfitting is where a model matches the training data almost perfectly, but does poorly in validation and other new data, like this first case. It did well almost perfectly because we used the same training data to train and also test the model. Right. That is why he performed very good. And the red line, it is a validation error. That's actually our boss line. This is what we are actually looking for. It shows error on new and unseen data. That's our validation data. It tells the truth about real world performance, and it first goes down and then up. That is what it does. So we have 2 zones. We have our critical zones. No, 3 actually. And our left side is our underfitting zone. And you know what underfitting is? Here, the tree is too shallow. It doesn't learn enough from the training data. And it is bad on both X and bad on both the training data and also the validation data. And then our right hand side is the overfitting. This side is the overfitting zone, and here the tree is too deep, learns the training data, but it doesn't generalize it, right? It is good on training data, but it is very bad on validation data. So basically, like the memorizer, a student who is a memorizer. We give a student a book. This child or this student can memorize everything in the book and answer it perfectly. However, if you give him or her new set of questions, the child wouldn't be able to get it. That is what the overfitting is. And underfitting is the clueless child, right? You give it a book, the child fails to find the patterns inside some related topics or question, probably statistics and algebra. They are quite alike, so but this child finds it difficult to find the patterns within it. So in this case, the underfitting is bad on the training data and then the validation data. However, the sweet spot, the middle, this is where we want, and here the training and the validation error is low, right? So this is what we actually want, right? We only trust the validation MAE, that is this line, and if it is too low, we have a good model. Otherwise, if it is high, we have a bad model, regardless of what our training MAE says. So here, this is our training MAE because we use the same thing to train and test. And we had a low value, but here we had a high value, but this is actually much more better than this because this we use the same training data for it and then we tested it using the same thing. Basically like giving a child some sets of questions to learn and then giving a child a book to learn and then you set questions from the same book word to word. Automatically the child will pass. But if we give it a new one, the child will fail because the child just memorizes. So this is what this one did. And this is a good child, right? This isn't just a memorizer. This actually learns using the training data and then is able to or make predictions using the validation data. Aside all this, right, we have a way of controlling the tree depth, right? If it is much deeper, we are running into the overfitting side. However, if it is low, we are also running into the underfitting side. So how are we going to solve this? We are going to do this using the max leave nodes argument, and it provides a sensible way to control the overfitting and the underfitting. So I'm going to write a code and then I will explain what the max leave node does. Max leave nodes, what I talked about to calculate the depth of our tree. So we inputted our library and we created a function named getMay with its parameters, the training mass and the validation and the max leave nodes. So inside a variable model, we call the decision tree regressor max leave nodes with our random state. So max leave nodes is what this is the parameter scikit-led expect, and this would connect it with the value inside our loop. So let's say here our max leave nodes we are using 5. So when we call our function the getMay here would automatically be 5 because let's say we are using 5. So 5 training x validation x train y and validation y. It would work out. Then it assigns it to this parameter with a random state because there for consistency. We then fit our model using the training data, we predict using the validation, we calculate our mean absolute error, and then we return it. Right? So that is basically what we did here. So as you can see, um, we are getting a monthly loan for 550, 500, 5,000. Yes, these are just a set of values that we use to calculate the depth of our decision tree regressor. However, there's also one step that is much better than a decision tree regressor. That is the random forest. Yeah, random forest. So that is what we'll be doing as our final step in this session. Then I quickly edit the codes, because as you can see, we've imported so many stuff. We've imported decision tree, whereas we've imported it in other space. So I just do it in a simple phase where I import everything at once, we write the code at once, and then we submit it to our Kaggle competition. For instance, is that it uses many trees, and then it makes a prediction by averaging the predictions of each component tree. It has a much better predictive accuracy than a single decision tree, and it works well with default parameters. So we will build a random forest model similar to how we built the decision tree in scikit-learn. But this time we will just use the random forest regressor class. Right. So that is what random forest is. So this is a sample code of what random forest is. We'll just edit certain parts of it for our code. So let's just build a random forest. So let me copy this. No, let me write it. So okay, so we use a decision tree, and then we use a random forest regressor, and we use it to calculate mean absolute error. If you compare the answer we are getting here to all of the answers here, you could tell that this is much better. So with our random forest, it is very good. It is better than a decision tree. So what I'm going to do next is I'm going to make some additions on this code, and then so that I don't repeat certain importations and all that, and I still arrange it in that order. And then I create a submission file. After that, I upload it into Kaggle. So that's what I'm going to be doing soon. So let's get it. Okay, so in this part, I created a new notebook, and I imported everything we need. I loaded the data, I prepared the features and then the targets, and the split data for the validation, I also used random forest. That is the best the best thing I should use as compared to the decision trees. And I trained a final model on all data for the competition I'll be submitting. So this is a model that calls life random forest regressive random city cost one. I think we've gone through this, and I loaded the test data and I made predictions for it. And this is the predictions made for the test data. This is the submission file named submission.csv. So this is just the code to ID test data.id. So prices. So this is the test spread, because according to the composition file should be in 2 columns. Let's just go. Go to the data tab and this sample submission. It should be in ID and then sale price. This is why we also have it in this. Let me name it. So I'm going to download my submission data. Okay, and let's make the submission. And let's see where we get to. Okay, let's submit. So initially we were at 2000 here. Initially my leaderboard was let me see where I am now. What? So I am now here at 2327. Initially I was at 7 something. No, I was at 4,000 there, believe, something like that. So, which means I still need to improve on it. I need to improve on it. So I make it to the first score. So the score should actually be 0.00. This is what it will be like. This is the main thing. But as we advance, I will get here because there are other things I need to learn. If you go here, you would be told that the intermediate machine learning course will teach you how to handle some types of features. These some features will throw an error if you try to use them to train your model. So this one will teach you the pandas course. I need to also do this to give me data manipulation skills and also the deep learning course. So this is how far we've come. And I mean, first I was at 7,000 something. I was beneath, and now I moved here. It is a great win for me. But as I advance, I will be able to, go to the top. So this is just it for today. Thank you all for